In this session, we will take up the reverse bias characteristics of a power diode. We will understand the two categories of power diodes. One is called as punch through, the other one is non-punch through diode. We will see why we call it as punch through and non-punch through. And then we will take up the switching profile, switching characteristics of a power diode. So that will be the agenda for today's session. In case this is just a standing instruction, in case you have any audio disturbance or any other disturbances, please stop me then and there. Don't wait for a long time. Please stop me then and there so that I can take suitable corrective action if needed. Now I'll start sharing my screen, and then we will first start with the reverse bias characteristics, followed by the switching characteristics of a power diode. Yes, I hope you can see the screen that I am sharing. Fine. Reverse bias characteristics. Reverse bias operation of a power diode. Okay. Now, when we tell reverse bias, this is a well-known fact. The terminals, namely the anode and cathode, they must be provided with a proper biasing, which means anode will be connected to the negative of the supply, while the cathode will be connected to the positive of the supply. And the supply, I name it as VAK, anode to cathode voltage, obviously. It is opposite to that of what we had seen in the forward bias condition. Now, because of this applied reverse voltage, there are certain processes that are going to happen. Again, you have to recollect that the moment junction is formed, there will be a depletion layer, which is going to extend across both sides the junction. And if you can recollect, we defined the depletion layer as the region or the layer where there will be charges, but they are not going to move. Immobile charge carriers. That is going to be the characteristic feature of a depletion layer. So this is depletion layer. I have not drawn the charge carriers, but if you want me to draw, it's fine. I will indicate that as well. So there will be immobile charge carriers. Space charge region will not have any charge carriers. The charges cannot move in the depletion region. This is going to happen the moment P plus and N minus junction is formed. Whereas this is the junction. I had indicated this in the previous session as well. Even today, I'll indicate for additional clarity. Now, under this state, we are applying a negative voltage. The negative polarity of the battery is connected to the, this is connected to the anode of the diode. Therefore, the applied negative bias will actually attract the holes away from the junction. Resultantly, the depletion layer will grow in thickness. So the moment negative bias is applied, the width of the depletion layer is going to increase. Width of the depletion layer increases, or you can understand that the depletion layer increases in thickness. Both are actually same. With we represented, I think WDP was the width of the depletion layer. Just any notation for our understanding, that's all. So that extended portion would mean this is going to extend over here, and you can expect such an extension on either side, which means on the left hand side or in the P plus layer and in the N minus layer. However, you need to understand that P plus layer is heavily doped, N minus layer is lightly doped. Therefore, the extension of the depletion layer in this n minus layer is going to be more pronounced as compared to the extension in the p plus layer because of excess charge carriers in the p plus layer. They are flooded with charge carriers, p plus layer, because the doping level is very, very high, 10 power 19 particles per cubic centimeter, impurities per cubic centimeter, whereas n minus layer is lightly doped. It's only 14, 10 power 14 particles per cubic centimeter. Therefore, the depletion layer extends into the n minus layer more compared to the extension in the P plus layer. This point you need to understand, that is because of the difference in the doping levels, difference in the concentration, doping concentration. I will indicate that as well. Resultantly, there is one more thing that is going to happen that we will understand now. Increases. I will write depletion layer extends more in the n minus layer. Depletion layer, I will write depletion region extends more the n minus layer than the p plus layer because of doping densities. I should write difference in doping densities, but I leave it here so that you will understand that, or because I am delivering a lecture, it is always a good idea to have your own notes and then note down the key point. I am not noting down all points. Yes, I'll be circulating notes, but notes will contain only 2 or 3 points. Later on, don't write those 2 or 3 points and claim full marks, because in between I am saying a lot of things, whereas I am writing only the key points. So it's always a better idea to maintain your own notes. Please note down the key points that I am saying, the processes that I am uttering. Depletion layer extends more in the n minus layer than in the p plus layer because of difference in the doping densities. One. Now, if we increase the reverse bias, let's say I apply a variable voltage, and then if I try to increase this applied reverse bias, more reverse bias, then the extension of this depletion layer will be even further. Okay, so at some point, depending on the thickness of the n minus drift layer and depending on the applied anode to cathode reverse bias, if the depletion layer touches this interface, then that diode is called as punch through diode. Whereas if the depletion layer does not touch, then that diode is called as non-punch through diode. That's all. So these are the two categories of power diodes: punch through diode and non-punch through diode. Right? That is what I was mentioning in the beginning. Now I'll indicate that as well. When the applied, I'll write when VAK is further increased, the width of the depletion layer also increases further. Now, due to the width of n minus layer is called as drift layer. That is a key point. I'll keep repeating this. Due to the width of the depletion layer and the applied VAK, reverse bias, the depletion layer can just touch the n minus n plus interface. just touches, it doesn't penetrate inside. That can't happen because of the applied reverse bias. So the depletion layer cannot penetrate inside the N plus, rather it can just touch that N minus N plus interface. Then such a diode is called as, this is punch through diode. The other category where it doesn't touch, you call it as non-punch through diode. This is one important classification of our diode, depending on the extension of the depletion layer into the N minus N plus interface. If that depletion layer touches that interface, punch through. Doesn't touch it, if it doesn't touch, non-punch through. That's all. Else, that is when if depletion layer doesn't touch, then the diode is non-punch through diode. It is not punching through, so it is termed as non-punch through diode. Okay, now these are the two broad categories. Now I'll tell one more point among these two, which is more advantageous, which is more preferred. Actually, punch through is preferred. It may, because when it may sound that punch through is a detrimental phenomenon. In fact, when I was going through this for the first time, punch through would mean the charge carriers are simply punching through that interface. How does one still consider the diode to be working when something has punched through, when the charge carriers have punched through? That was the impression which I got when I read this first. It is not actually punching through and then damaging the device in physical sense. That is not happening. The depletion layer just extends till that N minus N plus interface. That's all. It is not a detrimental phenomena at all. So punch through is actually more preferred, because if you don't want the depletion layer to touch this N minus N plus interface, if you want to stop the depletion layer somewhere here, if the user wants to stop the depletion layer somewhere here and doesn't like that punch through, then the width of the N minus layer should be made bigger. Then N plus layer should be thick. So when N plus layer, the thickness of N plus layer is increased, the resistance increases, forward voltage drop again increases. Therefore, compared to non-punch through structure, punch through diodes are, they are preferred. Let the depletion layer extend and touch the N minus N plus interface. Nothing detrimental is going to happen. It will still be having the blocking capability similar to a non-punch through diode. Therefore, the inference is punch through structures are preferred. Punch through diodes are preferred. I have told the reason.
Sir, may you please explain the reason once again?
I will. Fine. Now, the reason why punch through diodes, punch through structure is preferred is like this. See, if the user wants the depletion layer to be stopped somewhere here, wherever I am highlighting, then the width of the N minus layer should be made bigger. Only then the applied reverse bias will not be able to penetrate and touch the N plus N minus interface. Fine, which means the remaining portion, remaining width of the N minus layer is not utilized for blocking the applied reverse voltage. So the remaining, this width, that is not used for blocking the voltage, rather it is used for not touching this N minus N plus interface. That is non-punch through structure. Did you understand this point?
Yes, sir.
Fine. Now, because of this additional increase in thickness, there will be additional drop across this n minus layer. That is the drawback of non-punch-through structure. Therefore, people prefer having the n minus layer depending on the voltage blocking capability. Let the depletion layer touch the n plus n minus interface. Nothing is going to happen. The diode is not going to get damaged. Voltage blocking capability will remain the same because depletion layer cannot grow beyond it, beyond this n plus n minus interface because of the applied bias. That bias will prevent the depletion layer from penetrating further. That can't happen. But voltage blocking capability, that is reverse voltage, will remain the same. Because of the reduced thickness of n minus layer, voltage drop will be less. As a result, punch through structures are preferred. Is that clear to you now?
Yes, sir.
Fine, fair enough. That's all. These are the points with regards to the reverse bias condition and the two types of diodes, punch through and non-punch through diodes. I will pause for 1 or 2 minutes. In case somebody has got any doubt, please feel free to clarify. That causes additional power loss, right? So when you have please go ahead.
So will it affect the efficiency?
Definitely. Why not? You have an additional voltage drop across the n minus layer. Definitely it will affect the power conversion efficiency.
Okay, sir.
Any other doubt?
Like in the previous one, in the forward bias, we saw that the conductivity increases, so resistance decreases. So what happens in this case?
Okay, in a normal signal level diode, what will be the resistance in reverse bias case? Anushka, are you there? Were you able to listen to my question? I asked a question. In a normal signal level diode, what will be the resistance in reverse bias condition? What happened? Charge, I mean, for moving around and carrying current. Therefore, the resistance of the diode in reverse bias condition will be very, very high. But because there won't be any current flowing through the device, though the voltage drop is going to be high, the power dissipated is going to be less in reverse bias condition. So that is the answer to the question. What happens to resistance? The resistance is going to be high under reverse bias condition. That is a normal thing. Okay. Again, this is an interesting, I hope you are able to see my screen. It's a PowerPoint presentation. Again, this is an interesting topic because you might not have come across switching profiles of devices in your semiconductor devices and circuits codes. Whereas in power devices, they are going to be very, very important because in power devices, the one major difference between a power device and a normal device, I'm saying device generically because it's true for all devices, is the introduction of that lightly doped N minus drift layer. It is going to be present in all the devices. Now, because we are introducing an additional layer, the transients, switching times, they are going to be different. So one should definitely know how the device is switching. That is the reason why we are learning the switching characteristics of all devices. So you take any device. In fact, the first module is on power device. So in this first module, the pattern is going to be like this. Pattern means not question paper pattern. The study pattern will be, we will take a device. Let's say power diode was the first device. So in power diode, firstly, we will learn the character construction. What is the structure of the power diode? How is it constructed? That will be the first point. Second point will be the physics of operation. How does the device operate? And third point will be the VI characteristics of that power device. Fourth will be the switching characteristics. So these are the four things that we will learn with regards to any power device in module 1. So you take construction, operating principle, switching characteristics. Of course, operating principle, then comes the VI characteristics, and then the switching characteristics. So these are the 4 minor topics that you may have to go through for all power devices. And we have 5 or 6 devices. Power diode is one, power BJT is another, then comes the thyristor or SCR, MOSFET, IGBT. So 5 power devices, these 4 things: construction, operating principle, VI characteristics, switching characteristics. Module 1 over. Fine. So that is how we will be discussing. Now, for the power diode, the switching pattern, switching characteristics means the turn on and turn off profile. What is the behavior of voltage and current during turn on and turn off? That is what is called as switching characteristics. Turn on and turn off behavior, both. Turn on and turn off characteristics. These are called as switching characteristics. All right. Now we are taking a power diode. We are considering a power diode. Now, in a power diode, you try to recollect what happens, what are the processes that happened, physics of operation during turn on. So those processes will need some time to happen. Those times are going to contribute to turn on time and turn off time. That's all. This is switching profile. Now, in a power diode, can you tell what are the 2 features of power diode during turn on, 2 processes that happened during turn on? There should be some time, that's all. So these 2 time intervals contribute to turn on time duration, turn on time interval. Fine. Now we are just projecting, or we are trying to find out the profile of current through the diode, which is indicated as I of t, and voltage across the diode, which is represented as V of t. So first we will take up the turn on profile, turn on characteristics. So during turn on, first thing is the reverse turn on means the diode was in off state, which means it was in reverse bias condition. So first thing that should happen is the diode must be reverse bias on the diode. Diode must be, I will write FB, forward bias, which means the reverse bias must be overcome. So that time taken for the reverse bias to overcome, which means earlier the diode was blocking a reverse voltage VR. VR is the reverse voltage. The diode was blocking this voltage. So that blocking voltage must be removed, which means the width of the depletion layer must be brought down, must be minimized, and only then conduction can occur, can start. So that is what is happening during T1. Depletion layer, width of the depletion layer decreases and current begins to get established. So T1 is the time taken for the, I will write it as width WDEP, width of the depletion layer decreases. Okay, and it decreases exactly somewhere here. So once the width of the depletion layer is nullified, becomes 0, then the double injection process occurs. So this time, this portion is where the double injection just begins to happen. It is not complete, it is beginning to happen. So this is beginning of double injection. I hope you should be in a position to recollect double injection. There will be excess charge carriers injected into the P plus N minus junction from the left hand side, and there will be electrons injected into the N minus N place, N minus N plus, sorry, N minus N plus interface in the right hand side. So that is called as double injection. Or inside the N minus layer, there will be injection of holes from the left, from the P plus layer. There will be injection of electrons from the N plus layer. That is double injection. For this process to happen, it will take a time T1, first time duration. Then once double injection has commenced, it means the current through the diode is now ready. The charge carriers, excess charge carriers are now established in the N minus layer. Now the diode is ready to take up conduction, ready to take up the full current. So that happens next. So this current is going to be the forward current, which I will indicate as IF, the full forward current or the full current as demanded by the load, obviously. So once the excess charge carriers are established, T2 is the time during which both the processes, double injection and conductivity modulation, is complete. And IF is the forward current that the diode is going to carry. Sorry, spelling mistake. Forward current which flows through the diode as demanded by the load. So the moment conductivity modulation occurs, the resistance, what happens to resistance of the N minus drift layer? Due to conductivity modulation, what happens to resistance of the N minus layer? Please be attentive, please answer.
Decreases.
Decreases, good, decreases, good, very good. So what happens to voltage drop across the drift layer when the resistance decreases? Conductivity modulation decreases. No, conductivity modulation reduces the resistance. What happens to voltage drop?
Decreases.
It also decreases, right?
Also decreases, that's all. So that is what is observed. So earlier you had this peak and then the voltage drop actually reduces. Right? So T2 means the conduction is complete. The diode is able to carry the full load current. This is the steady state current, which means both the double injection process and conductivity modulation processes, they are complete. That's all. So this completes the turn on time interval. There is one significant difference between the signal level diode and the power diode. I will tell that. I will tell the reason for that as well. Turn on time is equal to T1 plus T2, or in other words, T time for turn on. T on would mean a different thing. So I will use some other, probably small t. Time for turn on is equal to T1 plus T2. That is the total on time. Now, the difference between the signal level diode and the power diode lies in this peak point. Okay. So this peak voltage, you will not see this. I will write it as peak voltage or spike in voltage. Not observed in signal level diodes. I will tell the reason as well. It's not observed in signal level diodes. The reason is, see, the depletion layer behaves like a capacitance. This is understandable. Depletion layer behaves like capacitance. I will call it as CDEP. Okay, and there will be stray resistance, stray inductance of the depletion layer. The stray inductance is mainly due to the contact leads. Contact that is made between the silicon wafer and the terminals due to the contacts. Now you have L and you have C. R is always there. So you have the resistance of the depletion layer as well. So RLC circuit, what can you expect in a RLC circuit? How will be the voltage behavior in a RLC circuit?
Oscillatory.
Exactly. Very good term. Perfect term. Compliments to you for that. That is why you see that peak. Right? So because you have depletion layer capacitance, because you have stray inductance of the depletion layer, they both interact and then the voltage profile is going to be oscillatory in nature. Therefore, that peak voltage is seen. In a signal level diode, you don't have this N minus layer. The depletion layer capacitance will be very, very, very negligible. Stray inductance will be much negligible. As a result, the peak voltage will not be seen in signal level diodes. That's all. This is one major difference that you need to understand. All right. So this completes the turn on mechanism, turn on process of the power diode. Next is turn off process. It is exactly similar to the reversal of the turn on process. See, in turn on, what did we do? Firstly, we removed the depletion layer, reduced the thickness of the depletion layer, and then conductivity modulation, double injection started. Then there was establishment of excess charge carriers. 3 points. So in reverse bias, again, there will be 3 points, but opposite. First of all, you have to remove the excess charge carriers, and then you have to make sure the depletion layer grows in thickness. Thirdly, width of the depletion layer should be able to block the applied reverse voltage. That's all, 3 points. These 3 points occur in 3 different time durations. T3 is the time taken for removing, time taken. Of course, this is turn off transient. Time taken for removing excess charge carriers. How do we remove them? They are removed using 2 methods. One is carrier sweep out. Sweep out meaning you simply wipe out the carriers by applying a large reverse bias. This is one. The other method is recombination. In the process of sweeping out, there will be recombination of holes and electrons. Therefore, that will also wipe out, or that will also, 1 minute, that will also, I'm trying to do many things at a time, therefore I am getting stuck. Fine. So I will first write and then I will speak recombination. So recombination is a process by which electrons and holes combine and then they get neutralized. As a result of recombination, excess charge carriers, they will be removed. So we remove excess charge carriers by carrier sweep out and recombination. So the time taken for removing the excess charge carriers is T3. As long as there are excess charge carriers, there will be voltage that is developed that is going to be available across the device. Right? Because excess charge carriers, when excess charge carriers are there, it means conductivity modulation is still happening in N minus layer. Therefore, voltage drop across the N minus layer will still be negligible. Therefore, the voltage across this is negligible. Right? Because we have removed excess charge carrier, the current through the diode comes and stays at 0. The moment there is no excess charge carrier, current will be 0. But now as the process stops, the answer is no, because reverse bias means the diode should be able to block, should be able to withstand reverse voltage. Fine. Now the device is not ready to take reverse voltage. Voltage is still power, positive. It's not negative, which means 2 other processes should happen. Now, when excess charge carriers are removed, it means depletion layer is not there, that's all. But depletion layer width should grow in thickness. Only then the voltage blocking capability and the reverse bias condition will be there. So that growth of depletion layer happens next, T4. T4 is the time during which depletion layer grows in thickness. I hope you are able to understand this because it is reverse bias condition turn off. So depletion layer width will increase, should increase. And that is completed at T equal to T4. At this instant, at time T is equal to T4, depletion layer completely is fully grown. Depletion layer is grown. The moment depletion layer is grown, voltage falls down to 0. Okay, and because of this depletion layer, now it is negative voltage. So voltage rapidly increases in the negative direction. And then the device is able to block the applied reverse voltage. This is the reverse voltage. Can you see this reverse voltage here? The same reverse voltage magnitude is this. Okay, now this is reverse voltage. The peak current that flows in the reverse direction, this is called as reverse recovery current, IRR. This is called as reverse recovery current. Reverse recovery current. And the time duration, T4 plus T5. TRR is called as reverse recovery time. This is equal to T4 plus T5. All right. VR is the reverse voltage. IRR is the peak reverse recovery current. You can call it as, sorry, not R. It is peak reverse recovery current. And you have this voltage as well. So this is called as maximum reverse recovery voltage or peak reverse recovery voltage, VRR. I'm not writing that, self-explanatory. So I'm not writing that. So you have these 3 or 4 distinct parameters. TRR, reverse recovery time, IRR, peak reverse recovery current, VRR, peak reverse recovery voltage, VR, maximum reverse voltage blocking capability. Reverse voltage, you tell reverse voltage, that's fine, blocking capability. Fine. So this completes the turn off process. Now, can somebody tell me what is the turn off time? Total turn off time. I will write it as T suffix turn off. Yeah. Any volunteers, please? How did we write turn on time? T1 plus T2 was turn on time. Now off time?
3 plus 4 plus 5.
3 plus 4 plus 5, correct. T3 plus T4 plus T5. This is actually turn off time interval. It may look silly, but let me see whether you are able to answer these things during CAT or some other purposes, or some other instance. See, you should be attentive because you might not have come across these things. And the moment you take a textbook and read, it will be very, very difficult. So please be attentive. That's why I'm saying. So this completes the turn off process of a power bank. That's all. Both combined together, that is turn on and turn off combined together, we call it as the switching characteristics. One point before I leave, there will be one, I will indicate in black. So you try to change, no? Try to use some other color. You try to refer a textbook based on which you will have good category or good, a simple expression with regards to the reverse recovery time. So you read Rashid and Nedmohan. I will circulate the relevant pages as well, not an issue, regarding snappiness factor and soft recovery diodes. There will be a small assignment based on this snappiness factor and soft recovery concept later on. So you try to read this. This will be Don't tell it has not been handled in class. The moment I write it here and I circulate these notes, mark it as important in green, it means self-explanatory. You read that how, based on the TRR, based on T4 and T5, how the diode is categorized as soft recovery diode or hard recovery diode. What should be the snappiness factor? Should it be less than 1 or more than 1 for a soft recovery diode? What is the difference? Things like that. Okay. On that note, I will stop. I'll wind up for today. In case